Hello, and welcome to the Raised Beaches podcast, a podcast about paleoclimate and global change. I'm Dr. Evan James Gowan, but you can call me Evan. This is episode 4 of the Raised Beaches podcast, and I'm recording this on December 25th. And as a result, Merry Christmas. This will definitely come out after Christmas, but I hope everybody had an enjoyable 2024. This episode, the deep dive, is going to be on the topic of Milankovitch cycles, which is one of the fundamental things that controls paleoclimate. So I hope you enjoy that. Of course, I would have liked to have made this episode a little bit more, a little bit earlier than this. My last episode was in early November, and one of the reasons it's taken a bit of time is that I've been working on a new reconstruction of the Eurasian ice sheets using a margin chronology known as dated 2. And this is being worked on by a number of colleagues, but it's led by Dr. Anna Hughes in University of Manchester. And I play a very minor role in this study to make the reconstructions. Deducing where the margin of the ice sheets were in the past is a complicated thing. You have to take into account the ages of indicators when the ice was gone, as well as the geomorphic indicators of the ice sheet geometry. So I've been working on that since October, actually, and I've made headway, of course, but hopefully by the middle of January, I'll have this mostly finished working, and I will be able to focus on this podcast a little bit more than I was in the past 2 months. Since my last podcast, there's been a few things that have happened. Number one thing is the autumn in Japan is came very late this year, and as a result, in the first weekend of November, my wife and I went to Okinawa to hit the beach, and the weather was absolutely perfect for that. And of course, when I go to the beach, I'm always interested in the geology, and specifically the geology related to sea level changes. And we were in this town called Yomitan, and in Okinawa, the main indicator of past sea level changes is a type of rock known as a beach rock. And beach rocks are all around Okinawa, and it's created by a process known as, or it's basically a cement where organisms secrete this chemical known as urea, which is the same chemical you find in your urine, and basically it cements all this material together. So if you look at the beach rock, it's full of coral and shell fossils, and this beach rock will form within a certain range of sea levels, so you can use that to infer the past sea level position if you measure the elevation of these beach rocks. And this beach rock, since it's basically a cement, has been used as a building material in Okinawa. And of course, I decided, has anybody investigated this to determine the past sea level in Okinawa? And the answer to that is yes. In 2019, a paper came out by Evelpido et al., and they went to all these beach rocks and measured their elevation, and also found the ages of them, and based on the analysis of the elevation or relative to mean sea level, they were able to deduce the past sea level changes, and coupling that with tidal notches, which are basically erosional features in rocks that are along the coastline, they were able to infer that in the past 5,000 years or so, there's been a drop of between 1 and 3 meters of sea level in Okinawa. And of course, I like to model sea levels, so I took those data and calculated sea level using my model PaleoMist to figure out what is the sea level change just due to glacial isostatic adjustment processes. And my model suggests that the sea level is pretty flat. So if that's correct, then it's possible that this change in sea level is a result of tectonics, which might make sense because Okinawa is located near a subduction zone. However, that could be wrong. My model could easily be wrong. So, as I mentioned in previous episodes, ocean siphoning is also a major reason why the sea level has dropped during the later part of the Holocene, and that could also be affecting the sea level in Okinawa. But right now, in terms of my own modeling, it's very preliminary. So I would not rule out that kind of process being responsible for this drop in sea level. And yeah, if you look at the tidal notches, there has definitely been a drop in sea level in Okinawa. So yeah, and yeah, Evilpedo et al. Also suggested that different parts of the island have a different magnitude of fall at sea level. So that also probably points towards a tectonic component to the sea level change. But at any rate, having 1 to 3 meters of sea level change over 5,000 years, in terms of tectonics, that's fairly moderate rate. So the second thing that occupied my time recently is a friend of mine from Germany came to visit me, and in Kumamoto, and I always like to take my guests to my favorite place, a viewpoint known as Daikambo. And what Daikambo is that in the center of Kyushu Island, there's a large caldera known as the Aso Caldera. And this caldera, which is basically a big bowl-shaped feature in the middle of the island, which formed after the eruption of a major volcanic eruption. Basically, this is one of the major features of the island. And Daikambo, you're basically at the top of this caldera, and you're looking down into the caldera, and it's absolutely wonderful to see, because if you're inside the caldera, it looks like you're surrounded by mountains, but actually you are inside of a big bowl, basically. So the Aso Caldera formed in 4 major eruptions, and the largest happened about 80,000 years ago, and that was probably the second largest eruption in the past 100,000 years. Nevertheless, the volcanic activity continues to this day, and there is a volcano in the middle of this caldera, and it occasionally erupts. It hasn't for a few years, but if you go there's steam coming out all the time. So that's one of the fun things to see in Kumamoto if you come to visit here. And another thing, like I said, the autumn has come quite late. Like it's December 25th right now, and there's still leaves on the trees, and usually they're fallen by the beginning of December, and this is caused by the fact that the ocean surface temperatures around Japan are quite warm, and there was a news program that I watched in November, and there's like a blob. There was a blob of water in northern Honshu, so sort of northern Japan, which was 6 degrees warmer than normal. And one of the consequences of this, because it is part of a longer term warming trend due to global warming, is that fish and other marine creatures are moving northwards. And in this program, they were talking about this really expensive crustacean, which they called a ise ebi, which in English it's known as a spiny lobster. Ebi in Japanese means a shrimp or a prawn, and yeah, I'd say it looks more like a really big prawn because it doesn't have the claws. But yeah, the meat ise is a very famous shrine in sort of near Nagoya, and yeah, it's called the Ise Ebi because they fished these crustaceans near this famous shrine. But now they're catching them in northern Japan, so they've sort of moved northwards, and they've become rare around Ise. And there's other tropical fish that they're starting to find in northern Japan. They're moving northwards, and in this program they also discussed that some of the fish that they're catching are dead because the water is too warm for the fish to survive. And this is a really major issue in Japan because of course they love to eat fish here, and the movement of fish to different habitats in different regions is one that they're having to deal with because it's happening very quickly. And the final interesting geologically related thing that I saw was Kumamoto University, where I have an affiliation, had a fossil exhibit for ammonites. So ammonites were a sort of a shellfish that lived in the water during the Cretaceous and Jurassic, and they went extinct 66 million years ago during the major die-off when the meteor asteroid hit Mexico at that time. And so these fossils are one of the most ubiquitous of fossils that you'll find in rocks, around Amakusa, which is very close to Kumamoto City. So they have a lot of these fossils. They're also found in Hokkaido. So there's a researcher at Kumamoto University who studies these. And some of these shells, like a typical ammonite fossil, you'll find it has a circular shell, but some of these have just crazy randomly shaped shells, and so they're very interesting. And some of them are quite big. Like they had one fossil that was about 1 meter wide, and I read that there's some ammonite fossils that are much larger. And I was told that in Japan, ammonites are synonymous with fossils. So, like even in Pokemon, the fossils look like ammonites. So that was interesting. I love looking at fossils. When I was a kid, I loved fossils and I collected them, and so I always enjoy looking at the fossils. And anyway, since it's the end of the year, I thought I would give a little bit of an overview of my busy year. So, yeah, at the start of the year, I was in Victoria, and one of the cool things I did in Victoria, which is in Canada, is I visited where I did my master's degree. And in some ways, it was kind of weird because not much had changed since I finished my master's degree, which was, I think, 18 years ago. So there was even a poster that had everybody who was working there, and I was on it. And so I had a good chuckle about that. And in February, I ran in a marathon, and I was training quite hard for that. And I also went to Seoul just for a fun trip. And in March, I went to Sapporo, and I met with Ralph Greva, who's the author of the Cyclops ice sheet model. So we're working together to do some ice sheet modeling, which hopefully I will finish early next year. And in May, I went to the Philippines, and that was kind of a vacation, but also got to see some nice coral reefs there. I went to Kobe, and I was visiting some of my friends from Canada who were staying there, and we went up the Roko Mountains. So Kobe, it's a really big city, but it's interesting because there's a literal mountain range that splits Kobe into two. So you can walk over this mountain range, which we did, and you go from one side of Kobe to the other. And there's of course a subway that connects the two sides of the city. And of course, I went to the Japan Geoscience Union conference, which I talked about in episode 1. So I always love that conference. It's a lot of fun. In June, I went to Canada, and I went to Buffalo, and I talked about Buffalo a little bit in episode 1 as well, where basically I was invited to discuss ice sheets and sea level there. And I was invited by Jason Briner, who's a very well-known geologist who studies the evolution of the Greenland ice sheet. In July, I went to Kikaijima. I was teaching in the summer school and investigating the sea level changes that can be deduced from the corals. In August, I went to Tsushima and Nagasaki, and I got to see some of the northernmost tropical corals that you can find there. In October, I also went to a different part of Nagasaki, and yeah, I discussed that as well, and how you could deduce some of the sea level changes there. And yeah, I already discussed my Okinawa trip, and yeah, one of the overarching things about this year is, despite being so busy, I am searching for a job, and I had one job offer, and I turned it down because it would require me to move to another country, and I decided, I'm getting too old to move around the world like that. So I'm looking for a bit more stability. And I did have an interview here in Japan, but it didn't pan out. And, it's sort of how it goes. And they're looking for something that maybe I can't fulfill what they're looking for. And of course that happens. But next year, I should be starting some lecturing at one of the local universities. So things are looking up for 2025 in terms of my job situation. And hopefully that builds up to something larger. And yeah, I expect in 2025, I will also make at least one trip to Kikaijima. And yeah, I probably won't do so much traveling in 2025. And, I think that's fine because I did so much traveling this year. And anyway, that is what's happened for me this year, and I had a good time, and I will hopefully. Oh yeah, the last thing. My Christmas present this year is that this paper, which I submitted on Christmas Day last year, was accepted for publication. So I'll be discussing that in an upcoming episode. So, and with that, this introduction is over. The deep dive of episode 4 of the Raised Beaches podcast is on Milankovitch cycles. Milankovitch cycles are the primary control on climate changes over this time scale of thousands to hundreds of thousands of years. And as a result, this is one of the fundamental components of understanding paleoclimate changes. So it's called Milankovitch orbital theory or Milankovitch cycles because it's named after the Serbian scientist Milutin Milankovitch, who's a Serbian scientist who came up with the theory in the 1910s and the 1920s. And at the time, that this was kind of controversial, and a lot of people didn't think that this was the cause of climate changes. But by the 1960s, there was starting to get really accurate proxy records from the ocean that did confirm that orbital variations were responsible for a lot of the climate change that we see in the geological record, at least for the past 5 million years or so. So Milankovitch cycles are composed of 3 different components: eccentricity, obliquity, and precession. And I'll go into more detail on what these things are. The first is eccentricity, and this is the component that has the longest time scale. So eccentricity is basically the shape of the Earth's orbit around the sun. And the Earth's orbit is an ellipse. So basically, one type of an ellipse is a circle where the Earth goes in a round circle around the sun, but that's not actually what happens. So basically, because it's an ellipse, at part of the Earth's orbit, the Earth is closer to the sun, and part of it's further away. And if the Earth is more eccentric, the amount of energy from the sun, the solar radiation, will increase as the Earth spends time closer to the sun and less when it's further away. And this eccentricity, the shape of the Earth's orbit, changes as a result of the gravitational attraction of other planets, namely Jupiter and Saturn. And over the course of this 100,000-year cycle, the difference between when the Earth is closest to the sun and furthest away will change the amount of radiation reaching the Earth by upwards of 23%. And this is not the full story because if you took high school physics, you probably remember Kepler's laws of orbital mechanics, and Kepler's second law states that when you are closer to the sun, the velocity of the Earth increases. So basically, even though you're closer to the sun, the amount of time spent close to the sun is less than when you're further away from the sun. So the part of the Earth's orbit when it is closest to the sun is known as perihelion, and when it's furthest away is aphelion. So at present, the southern hemisphere summer happens at perihelion. So the southern hemisphere gets more solar energy during its summer than the northern hemisphere. So the northern hemisphere summer happens when the Earth is furthest away from the sun. The second part of Milankovitch cycles is obliquity, and in terms of glacial cycles, obliquity is actually the most important component. And what obliquity is that the Earth's axis of rotation is on an angle relative to the plane of the Earth's orbit around the sun. And this angle is measured relative to the perpendicular line coming out of that plane of the orbit. So when the Earth's orbit is more oblique, that means that during the summertime, there's more solar energy reaching the poles. So when we're thinking about glaciation, the summer temperature is the most important thing that controls that, because during the summer, any snow that goes onto the land will melt during the summer. So when the Earth's orbit is more tilted or when the axis of rotation is more tilted, that will mean that more snow will melt. And as a result, if the axis of rotation is less tilted, ice can accumulate on the surface, and you'll develop ice sheets. This varies over a period of 40,000 years, and the changes between 22.1 degrees and 24.5 degrees. Now, that doesn't sound like much, but that small amount is sufficient to change the duration of the summer and the intensity of the solar energy reaching the northern hemisphere polar regions enough to create these ice sheets. And the cause of obliquity is due to the gravitational attraction of the planets and the sun. And yeah, so the third component of Milankovitch orbital theory is precession. So the Earth's axis of rotation precesses like a top. So basically, the direction the Earth's axis of rotation points relative to the plane of the orbit will change over time. So, as an example, right now the Earth's axis of rotation, the North Pole is pointing towards the star Polaris, but in a few thousand years that will not be the case. And the consequence of this precession is that the place in the Earth's orbit where the summer or the winter will happen will change over time, and that happens on a period of about 26,000 years. So this is created because the Earth is not a sphere, and it also has the axis of rotation is tilted relative to the plane of the Earth's rotation around the sun. And as a result of the fact that the Earth is kind of bulged out near the equator, that the gravitational attraction of the sun will exert a torque on the Earth, and that's what's causing this precession. So right now, as I mentioned, the southern hemisphere summer is happening when the Earth is closest to the sun, but in 13,000 years from now, that will be reversed, so that the northern hemisphere summer will happen when the Earth is closest to the sun, and of course, the consequence of that is that it will be less likely for an ice age to start, glaciation to start in the next 13,000 years. And of course, like I said, everything is based on the northern hemisphere summer, because the northern hemisphere has continents, and snow will come on it, and depending on the amount of snow that melts, it will change many other parts of the climate system, like how much solar energy is being reflected back into space. And the southern hemisphere is mostly ocean, so it's not as the orbital cycles are not so important on the southern hemisphere conditions. Over the past million years, there's been very large changes in the intensity of the solar radiation in the northern hemisphere, and based on the paleoclimate proxy records, we see periods when the amount of energy reaching the northern hemisphere polar regions in the summer, you do see the growth of ice sheets, and opposite when the amount of solar energy reaching the northern hemisphere increases, then you see a retreat of the ice sheets. And right now we're in a situation where there's only ice sheets in Greenland, and but yeah, 20,000 years ago there was ice all over North America and Europe. So 20,000 years ago, that was that's probably coincides with when obliquity was sort of at a minimum. And last episode I talked about proxy records, and specifically the LRO4 curve. And the LRO4 curve, which goes back about 5 million years, you see this fluctuation in the oxygen isotopes. And the oxygen isotope variations are dependent on the temperature of the ocean and the amount of ice on land. And when they decomposed this signal between about 2.5 and 1 million years ago, you do see the influence of the obliquity, and the fluctuations have a time period of about 40,000 years. But after 1 million years ago, that amplitude changed, and the duration of these cycles changed to be about 100,000 years, which is what eccentricity is. And the reason for this is not quite understood yet. It's probably a feedback in the system, and this is something that is being actively discussed. It could be related to greenhouse gases, for instance, but we don't have a record of carbon dioxide going back that far back in time. But hopefully in the next decade we will, and maybe it's something more simple, like a change in the configuration of the land where the ice sheets grew. That's another possibility. So anyway, there's still this strong 40,000 year effect, even the past million years. But the magnitude of this LRO4 curve, which is the most important proxy record, does show this orbital variability quite well. Another famous proxy record that demonstrates the orbital influence on climate is the Chinese speleothem record. So a speleothem is a cave rock, and if you measure the fluctuations in oxygen isotopes, it tells you about the conditions of precipitation where the cave is. And the fluctuations in the oxygen isotopes in China are influenced by the monsoon, the Eastern Asian monsoon. In simplistic terms, monsoon is basically an effect of the global wind patterns, which are affected by the gradient of the temperatures between the polar region and the equator. So basically the position of the monsoon will change as the intensity of the northern hemisphere summer changes. So it fits so well. It's really quite amazing, and it does show that the orbital changes are responsible for a lot of the climate change that we see in the paleoclimate records. So into the future, if there was no changes to greenhouse gas emissions, we're actually moving into this period where obliquity is decreasing, which would decrease the intensity of the northern hemisphere summer. But we're also at the same time going into a period where, because of precession, the summer is slowly moving towards having the northern hemisphere summer when the Earth is closest to the sun, and these sort of effects are canceling each other out in the next 10,000 years or so, and so as a result, in terms of the orbital theory, we were probably in a period of time in recent Earth's history where, absent of humans, the climate should be quite stable, which this hasn't really happened in recent Earth history, where there's a long period of no northern hemisphere glaciation for probably several tens of thousands of years. And the last time this may have happened was about 400,000 years ago, and that was a period where sea level was quite high, and also the global climate was also quite warm. And in the absence of human activities, the next glaciation would probably be delayed for a while, and this eventually the glaciation would start. And I have not done any climate modeling to confirm when it might start, but I think we would have been in a very long non-glacial period, and it would probably start about 50,000 years from now, which is quite late. But when it does start, it would probably start quite abruptly, I think. So that's interesting to ponder. But when we think about paleoclimate, we want to think about what happens in the future, and this is one of the things that we have to ponder. Anyway, that's the deep dive. Okay, now that we've finished the deep dive, I'll discuss a few more topics related to Milankovitch cycles. Of course, Milankovitch was not the first to propose that paleoclimate changes were a result of changes to the Earth's orbital conditions. First person to do that was James Kroll, who was a British scientist, and he proposed this in the 1800s. And based on some of the calculations of the Earth's orbital changes, he proposed that eccentricity would be the strongest control on climate changes. The reason he said this was that because of the changes on how close the Earth was to the sun, that it would change the strength of the Gulf Stream, and that each side of the Earth would, or each hemisphere of the Earth would change the strength of the current going from the equator to the pole. So right now we're in a situation where the Gulf Stream is quite strong, and he assumed that when the Earth's orbit was such that the southern hemisphere was closer to the sun, that would change the current so that it went southwards. And as a result, he also proposed that the glaciations would be asynchronous between the northern and southern hemispheres. And this idea was not accepted by a lot of scientists, but one scientist who thought it was a great idea was Charles Darwin in the origin and in the Origin of Species. He talks about this. So Charles Darwin in the Voyage of the Beagle did a lot of work in South America, and he did a lot of observations on the glacial geology in Patagonia, and he noted that while there was an ice age in Patagonia, and there was an ice sheet similar to what there was in Europe and North America. And he also was looking at how the tundra species, like the plants and animals, are quite similar in Patagonia as they were in Europe. So he thought this was a great idea, this orbital theory by Kroll, and you know, I'll read you the paragraph that he wrote about it, and he's like, from these several facts, namely from the glacial action having extended all round the northern and southern hemispheres, from the period having been in a geological sense recent in both hemispheres, having its lasted in both a great length of time, as may be inferred from the amount of work effected, and lastly from glaciers having recently descended to a low level along the whole line of the Cordillera, it at one time appeared to me that it could not avoid the conclusion that the temperature of the whole world had been simultaneously lowered during the glacial period. But now Mr. Kroll, in a series of admirable memoirs, has attempted to show that a glacial condition of climate is the result of various physical causes brought into operation by an increase in the eccentricity of the Earth's orbit. All these causes tend towards the same end, but the most powerful appears to be the indirect influence of the eccentricity of the orbit upon ocean currents. According to Mr. Kroll, cold periods regularly occur every 10 or 15,000 years, and these at long intervals are extremely severe, owing to certain contingencies, of which the most important, as Sir Charles Lyell has shown, in the relative position of the land and water. Mr. Kroll believes that the last great glacial period occurred about 240,000 years ago, and endured with slight alterations of climate for about 160,000 years. With respect to the more ancient glacial periods, several geologists are convinced from direct evidence that such occurred during the Miocene and Eocene formations, not to mention still more ancient formations. But the more important result for us, arrived at by Mr. Kroll, is that whenever the northern hemisphere passes through a cold period, the temperature of the southern hemisphere is actually raised, with the winters rendered much milder, chiefly through changes in the direction of the ocean currents. So conversely, it will be with the northern hemisphere, whilst the southern passes through a glacial period. This conclusion throws so much light on geographical distribution that I'm strongly inclined to trust it. But I will first give the facts which demanded an explanation. So, Charles Darwin really liked this idea because it explained some of the distribution of species, which he described in The Origin of Species. However, there were problems with Kroll's idea, and the main problem is that Kroll proposed that the last ice age ended over 100,000 years ago, and the issue was that even by the relatively crude dating methods they had for geology in the 19th century, this was too long of a period. As an example, Niagara Falls, the erosion rate of Niagara Falls was fairly well established, and they said, well, if the ice age ended that long ago, Niagara Falls would not be there because it would have eroded back to Lake Erie. And anyway, it was also very clear that there was the northern and southern hemisphere glaciations probably happened at the same time. And the main thing that really discredited Kroll's ideas was the hypothesis by Svante Arrhenius in 1896 that the climate changes could be explained by changes in carbon dioxide, and he provided a detailed calculation of that. So when Milankovitch came back in the 1910s and 1920s and said, no, look, the orbital variations are what's causing these interglacial cycles, it met with a lot of resistance because this carbon dioxide proposal by Arrhenius seemed to work quite well. And anyway, it wasn't until the 1960s that we started to get these oxygen isotope proxy records from the ocean that we were able to confirm that Milankovitch theory was actually the main control on glacial and interglacial cycles. The second reason we know that Milankovitch theory actually works is that the Earth is not the only place that is affected by Milankovitch cycles. So Mars also has changes in climate due to changes in the orbit. So right now, Mars you can see it has ice caps on the North Pole and the South Polar regions. But Mars had an ice age, and it actually has ice ages in the opposite sense of the Earth. So when Mars's obliquity angle is much higher, then that will cause these polar ice caps to melt, and that will cause the ice to go to a more equatorial region. And Mars has much larger variations in obliquity than the Earth, and in the past 10 million years it's been calculated that it has varied between 14 and 48 degrees, which is compared to Earth's 22 to 24 degrees. It's a lot larger, and it's kind of erratic. So obliquity is kind of a chaotic feature. So up until about 5 million years ago, Mars was in this regime where the obliquity varied between about 25 and 48 degrees. But in the past 5 million years, it sort of abruptly changed and went down to between 15 and 35 degrees. This step change, it's interesting because it's a consequence of general relativity, and it serves as one of the proofs that general relativity is affecting orbital motions. And anyway, if you look at the surface of Mars, there's evidence that there were glaciers, and we know these are geologically recent because most of Mars is covered with craters from meteor impacts, but these glacial features, or these features that look like glacial features, don't really have any craters on them. And if you look at it, it looks very much like what it looks like if a glacier melts on the Earth. You'll find like a ridge towards the bottom of where the glacier was, where there's an accumulation of sediment. And there was a paper written by Head et al., and they proposed, based on the obliquity of Mars, that the most recent Martian ice age may have ended as recently as 400,000 years ago. And it's pretty amazing to think about that the surface of Mars, which, years ago they thought that Mars was kind of a dead planet, but there's actually geomorphology, active geomorphology impacting Mars in the same way as Earth in terms of glaciation. So, yeah, Milankovitch's theory, it works not just on Earth, but it also works on Mars. So maybe someday in the future we'll be able to go to Mars and take samples and date when this glaciation happened, which is possible using cosmogenic isotopes. Something I'll talk about in a future episode. All right. So, for the paper section of episode 4 of the Raised Beaches podcast, I'm only going to highlight one paper. And the reason for that is I'm a co-author on this paper and I have a bit to say about it. And this paper, which was led by Carla Rubio Sandoval, is entitled Quaternary and Pliocene Sea Level Changes at Camarones, Central Patagonia, Argentina. And this was published in the December 2024 issue of Quaternary Science Reviews. So, first off, I've discussed this in past episodes, but in 2019, I went to Patagonia to participate in some field work to determine past sea level changes in Patagonia and Argentina. And I participated in this field work, and it was a great experience. And one of the places we went to was a village known as Camarones. And Camarones has a big sign that says it's the national capital of salmon. But if you know Spanish, Camarones actually means shrimp. So one of my cousins said, "Oh, did they run out of Camarones? Why are they the capital of salmon?" And I have no answer to that. But anyway, we went to do these surveys as part of the Warm Coast Project, which was led by Alessio Rovera. And this was funded by the European Research Council under the European Union's Horizon 2020 Research and Innovation Program. And the purpose of the Warm Coast project was not simply to collect new relative sea level data. It was actually to go back to sites that had been surveyed before and try to get more precise measurements using modern techniques. So that is why we went to Camarones. So the deposits past higher sea level have been well studied, but we went back with a GPS and we collected more samples to get more precise age constraints. So that is why we went there. So Camarones is located in central Argentina, and it's, of course, on the Atlantic side of South America. And if you've never been to or if you don't know anything about Patagonia, it's kind of a desert. And because it's a desert, these shoreline deposits, which were deposited hundreds of thousands of years ago, and in one case much longer ago, are quite well preserved. So because of the preservation, it's been the subject of study for going back a long time. Like Charles Darwin went there, and he didn't specifically study at Camarones, but he did study these raised shoreline deposits in different places. This is the Raised Beaches podcast, so it was interesting to go to these raised beaches. And this specific location at Camarones is interesting because it has evidence of shoreline deposits, raised beaches, and whatnot at 4 different time periods. And because we're far away from the west coast of South America, we would not expect tectonics to be a major contributor to these raised beaches. Like if you go to the Chilean side of Patagonia, you find shoreline deposits, tens to hundreds of meters above present, which are much younger than the deposits that we studied. So this is we're going into this with the assumption that tectonics are quite minor. One of the things that Carla was working on is to determine what is known as the indicative meaning of beach ridges. So some of the shoreline deposits that we study here are beach ridges. And what a beach ridge is that they're basically a deposit that is pushed on shore by the action of waves during storms. So these usually will form a little bit above sea level, but the precise position of sea level relative to these beach ridges was not well established before this study. So basically what we did is we calculated the statistics of the wave heights, so going back a couple of decades using satellite measurements, and then used a modern analog of where you find shells on the modern beach ridges, and was able to calculate a relationship between where you find shells in a beach ridge versus where sea level is. And then you go back to these ancient beaches, and you find the elevation. You measure with GPS the elevation of where these shells are found, and then you can tightly constrain what the sea level was when these beach ridges formed, and you can determine the relative sea level changes. So, in the field work we did, we went with the GPS and measured these where these occurrences of these shells were, and also different features in these deposits. And we collected some shells, and it's really interesting because these deposits are very gravelly, but you'll find these like perfectly preserved shell fossils in them. And it's really amazing that you can have a situation where you have this gravel, but then the fossils were not destroyed during the deposition of this gravel. So there's so many shells. As a kid, I was obsessed with fossils, and I mentioned that in the introduction that I love fossils, and it was pretty cool to see all these fossil shells. So collecting these shells, you can find the age of the deposit by measuring various properties of these shells. So the past studies use techniques known as uranium thorium dating and electron spin resonance, and these two techniques sort of rely on measuring the amount of uranium in the shell, and but the issue is that uranium can leak out of the shell, or it can get incorporated into the shell after the mollusk dies. So you have to make a lot of assumptions about how much uranium is going in and out of the shell over time. So the uncertainty on the ages is quite large. So instead, we were using a technique known as amino acid racemization, and we were applying it to a species of mollusk known as Amyghinomia antiqua. These Latin names are kind of a mouthful, and but these kinds of shells are found all along the coast of Argentina, and you find them in the shoreline deposits of different ages. So ideally, with amino acid racemization, you want to use the same species of shells, and what this is an amino acid is an organic molecule, and basically after the mollusk dies, certain types of amino acids will change its form, and this is dependent on the amount of time that is elapsed and the temperature conditions, and based on the ratio of different types of amino acids, you can determine a relative age, because this relationship in changing the form of the amino acid molecule, it happens in a very regular way. So yeah, you can use this to determine if the deposits are of different age. And yeah, we use this to complement these other dating techniques that have been applied. And when we checked the amino acid racemization results, we compared, of course, modern shell, like a shell that we found on a beach right now, and compared the ratio of these different types of amino acids. And yeah, we basically, we know there are 4 different ages of the deposits, and yeah, we can definitely tell that there's a difference between the ages of the second and third highest beaches relative to the Holocene beaches or shoreline deposits. But what was interesting is that the second youngest set seems to have a much broader range of ratio values, and this could possibly indicate that during the period known as marine isotope stage 5, there might have been 2 periods of relatively high sea level, and that introduced shells of different ages into the same deposit. So now I'll go into an overview of the 4 different deposits, starting with the one that has the highest elevation and is the oldest. So the highest one is Pliocene in age, and this was investigated in detail by Rovera et al. 2020, and they had to use a different dating technique, but they calculated that this shore platform probably formed between 4.7 and 5.2 million years ago. And based on the elevation and the geomorphology of this deposit, they inferred that sea level was, the relative sea level was 36 meters higher than it is now. And this seems kind of high because based on what we know about ice volume, it seems unlikely that global sea level was 36 meters higher than it is now. So they infer that there's a component of glacial isostatic adjustment and also dynamic topography, which I talked about in the sea level episode, or in the first episode about raised beaches. So yeah, basically there has been some level of uplift here in the past 5 million years, but it can't be more than maybe 15 to 25 meters. The second highest and the second oldest beach has an inferred paleo sea level of 14.5 meters higher than present. And the age of this is a bit ambiguous, but based on the information we have, it happened between 300 and 420,000 years ago. And this time period encompasses 2 interglacials known as marine isotope stage 9 and marine isotope stage 11. And so marine isotope stage 11 is associated with the warmest conditions and in some places the highest sea level that has happened in the past million years. So based on that, we sort of might expect that this is probably from that time, but some of the age constraints seem to suggest it's actually young or more recent than that. So that'll be the subject of some glacial isostatic adjustment modeling. So the second youngest is in marine isotope stage 5, and like I mentioned, there's the possibility that there might have been 2 periods of high sea level during this time. So marine isotope stage 5 happened between 80 and 130,000 years ago. And the period with globally high sea level is the last interglacial period, which was 115 to 130,000 years ago. So it seems obvious that should be the high period, but based on the amino acid racemization results, it seems like that could have been one period, but there's also the possibility that in 80,000 and 100,000 years ago, there was also relatively high sea level, and maybe there's some shells mixed with this. Based on the deposits that we measured, the relative sea level of this deposit is 8.7 meters higher than present. Yeah, I'll talk about this in a second, but it's not so much higher than the high stand in the Holocene. So that also might give a bit of indication that this younger part of marine isotope stage 5 might have been able to get to this level. This 8.7 meters seems to be on the higher end of the estimates of last interglacial sea level high stand. In the Holocene, we were able to get some shells to radiocarbon date the highest part of the Holocene high stand, and based on those radiocarbon dates, it seems that the high stand happened between 2,600 and 3,400 years ago, which seems pretty recent. So around the world, the Holocene high stand tends to happen like 5,000 to 6,000 years ago, and even along Patagonia, it seems to be a bit earlier than that. But what's interesting is that the Holocene beach ridges, which are very different color than the older ones because they're much more recent, has an inferred sea level high stand of 6 meters. So what it's suggesting is that there's been a 6 meter drop in sea level in the past few thousand years, and the 6 meters is only 2 meters lower than the MIS5 sea level high stand. And the reason why the high stand is so high in Patagonia, and this is true along the entire coast, is a result of glacial isostatic adjustment. Basically what happened is when you had the ice sheet pile onto the North America and Europe, that affected the Earth's orbit and also changed the Earth's gravitational field a bit. And when that ice melted away, of course, the water initially flowed to the southern hemisphere, and as the Earth was rebounding after the delayed isostatic rebound, some of that water goes back, but it also was changing the rotation of the Earth a bit, and this effect is quite strong in Patagonia just because of where it is relative to the ice sheets in the northern hemisphere. So I did some modeling of this, and other people have also done modeling of this, and it seems to confirm this idea that yes, the high stand in the Holocene and probably the last interglacial is a result of glacial isostatic adjustment. And right now, Carla, who's the lead author of this, is working on a broader database of past sea level changes in South America, and we'll be able to get a much better pattern of the changes due to glacial isostatic adjustment and be able to model that. And that's, of course, something that I plan to do in the future. So stay tuned. Next year, there will be another paper coming out on this topic, and we'll see about modeling the sea level changes in more detail. So that's it for episode 4 of the Raised Beaches podcast, and I'll see you again in 2025. Thank you for listening to the Raised Beaches podcast. If you enjoyed this, please follow my social media accounts, where I post more information on the paleoclimate sciences. I am on Mastodon with the username @DrEvanGowan@FetiScience.org. On Blue Sky, my username is @evangowan.bsky.social. On LinkedIn, my username is Evan James Gowan. I hope you tune in next time. Thank you.